Hey everyone, so I want to talk about the very last topic in this dynamics unit, which is all about accelerated reference frames. Now, for the most part, we have sort of talked about this, though I haven't given it the exact phrasing. One thing I do want to point out is that despite its name and the description that I'm about to give, it is very straightforward and very simple. So, what is an accelerated reference frame? Basically, the idea is that you, an observer, are in a are observing an object, and while you're observing that object, both you and the object are accelerating in some way. Because you and the object are accelerating together, there's really no difference between you and the object. So everything that we end up noticing almost seems like it violates the laws of physics. So some perfect examples of this are essentially when you go in, well, I guess when you go into an elevator and you stand in there, all of a sudden you'll start to feel forces pushing down on you or pulling up on you. If you didn't know that the elevator was moving, you would just think that magically forces started acting on you for no reason. That's an example of an accelerated reference frame. Another example is if you drive in a car and you have something hanging from your rear view mirror. As you turn the wheel or you accelerate or decelerate, you'll notice that that thing that you hang will end up moving side to side, front to back. It'll move around based off of how you move your car. Again, if you weren't paying attention to what's going on outside, you would think that that violates the laws of physics because all of a sudden, this object that was initially at rest starts moving. What's going on? There's unbalanced forces, and objects at rest shouldn't have unbalanced forces. But the whole idea is that once you take into account the the reference frame and that it's also accelerating, you'll understand that those forces are coming from some known place. One example would be the gravitron. If you've ever been on one of those rides over at the fairs, you go into a room, it spins around. That's another example of an accelerated reference frame. While you're in there, you can act differently because it's accelerating versus when it's not accelerating. Now, for the most part, when we say accelerated reference frames, we're mainly going to be referring to elevator rides. So that's kind of going to be the big example here. All right. Like I said, the main well, one thing to realize is that when you're in a reference frame and that reference frame is accelerating, it's going to seem as if Newton's laws don't hold true. I said this before, but what that really means is that we have to take into account the frame as well to understand where these, you know, um, forces are coming from. So let's look at this. We have an elevator that's at rest, and we want to know what are the forces acting on us. Well, we know that there's a gravitational force pulling us down, and there's a normal force pulling us up. Remember, we're only looking at ourselves in here. Now, we are both the observer and the object in this case. Now, are they balanced or unbalanced? Well, since I am at rest, not only am I at rest within the elevator, but the elevator as well, I know that these two forces have to be balanced because of Newton's first law. Similarly, for this next one, where the moving at a constant velocity, again, uh, that's another example of being in equilibrium. So my normal force should equal my gravitational force again. So that's it. All right. Now let's look at the case where we're accelerating upwards. Well, we still have the normal force and the gravitational force. Those two forces don't change. So we have a normal force and a gravitational force. Now, even though I am still at rest in the elevator, because my reference frame, the elevator itself, is accelerating upwards, I also have to consider that I am accelerating as well. So if the elevator is accelerating upwards, I'm also going to accelerate upwards. Now, the question is, are these balanced? Well, since I know that there is an acceleration and the acceleration's upwards, I know that they are not going to be balanced. And in fact, I know that that normal force has to be the bigger force in order for me to get an upwards acceleration along with the elevator. And then the force that's unchanged is the force of gravity. Because remember, our weight does not change as long as I'm on Earth. As long as I stay on Earth, my weight should not change. All right. So we'll do a quick practice question with this. So again, when you accelerate upwards, your normal force will be bigger, but your weight doesn't change, and your net force is also going upwards. All right. So here's a practice question. Pause video, work yourself. I'm going to go over in a second. All right. So we want to know what the forces that are acting on the 80 kilogram man. Well, we know the gravitational force is going to be the 80 times 10. So Fg is going to equal to 800. To find the normal force, I'm going to have to do sum of the forces equals ma. So we have the normal force minus the gravitational force. Because of the fact that I'm accelerating upwards, I know that the force that's going up, the normal force, has to be positive, and then the gravitational force has to be negative. So I move the force of gravity over to the other side. Remember, I'm going to try to solve a little bit more algebraically. So Fn is going to be equal to the mass times the sum of the accelerations. So my mass is 80, and both my acceleration caused by gravity and the acceleration caused by the elevator are both 10. I'm going to end up getting that my normal force is 1600 newtons. So I end up feeling twice as heavy as I would at rest. All right. Now for the downwards case, let's say that we're accelerating downwards. Again, the forces are the same. So I draw my FBD, the normal force goes up, the gravitational force goes down. Because I'm accelerating downward, I know that, again, they are not going to be balanced. And in fact, the gravitational force must be bigger than the normal force. Once again, it's important to remember that your force of gravity does not change. So throughout this entire process, Fg was constant. What that means is normal force actually got lower. It became a smaller value. So just keep in mind that the normal force is the one that's varying. So again, accelerate downwards, the normal force becomes smaller, your weight remains the same, and the net force is also going down. All right, so here's the next question. Pause the video, work itself. I'm going for a second. All right, we'll do the same thing. We want the forces. Fg didn't change, so that's still going to be 800. Do the sum of the forces. This time, though, I have to make sure that I do Fg minus Fn. It is extremely important that when you do these elevator rides, that you get into the habit of putting the forces in the correct orders. Because if you don't do that, you'll end up getting the completely wrong answer. So plugging this in, we end up getting that now it's going to be m times the difference in their accelerations. Since both my acceleration in gravity and the acceleration of the elevator are both 10, then that means my normal force actually ends up being 0. So what's going on in this case? Essentially what this is both me and the elevator are in free fall. And because the ground is now falling below me at the exact same rate that I'm falling, I don't have a normal force anymore. There's no, connection between me and the floor because the floor is pulling away from me just as quickly as I'm going towards it. This actually is a very important aspect, mainly for Hollywood. The way Hollywood tends to do a lot of um, recordings for people being up in space, like in movies. They put people into what's called a vomit comet. It's a plane that's, completely padded all over, and it basically flies people up into the air and then does a little nosedive for a bit, accelerates at the same rate of as acceleration, and the people will actually start, floating around, and it will look very similar to as if they're in space. So if you want, you can watch this, just a YouTube video of people experiencing the vomit comet. All right, now the next thing I need to talk about is this the idea about apparent weight. So I didn't mention this already, despite what this says, but there's a difference between your apparent weight and your actual weight. So, for example, when you free fall, when you fall out of a plane, your weight, the weight that you actually have, is different than the weight that you're feeling. You actually feel weightless. It doesn't feel like you weigh anything. You almost feel like you're floating. But we all know that since you're still on Earth, there has to be an FG value. If you go off into ISS, even though again you're floating in air, you feel weightless, you feel like you don't like there's no gravity on you. There is still technically a force of gravity. It just doesn't feel like there's a force of gravity because of how you're moving. But you do have a noticeable gravitational force. So it turns out this idea about apparent weight is that it's actually the normal force that we're feeling. When we think about how much we weigh and we think about ourselves weighing more or weighing less or being completely weightless, what we're really saying is that the normal force is more or less or not at all. So we actually don't notice the FG value, we notice the normal force. This seems a little bit weird, but again, if you go into an elevator, as we mentioned, during the ride, the normal force is the one that's changing. Well, we know that when we go into an elevator and it accelerates upwards, let's say, we know that we start to feel almost like a force pushing us down, and it almost makes us feel heavier. If we accelerate downward, we feel the force kind of lifting us up, and we'll end up feeling a little bit lighter. If you go onto any ride and do this, you'll feel heavy or lighter depending on how you move. So again, it's the normal force that we're experiencing. And it turns out the scale, if we ended up standing on a scale, like what measures weight, it would actually not measure our actual FG value, but it measures our normal force. Again, this kind of makes sense when you stand on a scale. You know, it measures a number, but if I push down on you, I don't change your weight because I'm not changing M or G, FG equals mg, but I am adding an additional downward force. So the normal force, the force that the scale is providing, has to balance both the FG force and this additional applied force. So it's important to remember that when you see the word apparent weight, the feeling of weight, a scale reading, they're referring to the normal force. All right, so let's work on this question. Pause the video. Work on yourself. We'll go over in a second. All right. So they want us to figure out what direction the elevator is accelerating in. Well, I know that my weight is going to be 950 newtons. I know that the scale reading is 200 newtons. That's my normal force. So because the force of gravity is greater than the normal force, then we have to have the elevator going downward, because that downward force is bigger. For part B, finding the actual acceleration. Well, again, we're going to do some of the forces in that y direction. So we do Fg minus Fn. Again, the gravitational force is the bigger one. Plug our numbers in, and we end up getting that the acceleration is 7.9 meters per second squared. So the elevator is accelerating downward at this rate, a little bit less than gravity. Now, the next question is the elevator moving upwards or downwards? Now, the answer is we don't know. There's not enough information in this problem. It's important to remember that when we talk about the forces, if I give you only information about the forces acting on the object, we can only identify the direction of the acceleration. We cannot determine the velocity without any more additional information. So we would need to know things like, where's the elevator starting? Is it starting at the bottom of the ground, or did it start at the top? We'd have to know what's going on with the speed. Is the speed increasing or decreasing? Because if it's increasing, we know that the velocity and acceleration are in the same direction. If it's decreasing, it's opposite directions. We would need to know whether it was starting off, like did I go onto the elevator and then stand on the scale, or what has the elevator been moving and then I stand on the scale and it's coming to its stop. So I would need something more about what the elevator is doing before I can determine whether or not it's moving upwards or downwards. All right, here's the next one. Pause the video, work on itself. We'll go over in a second. All right, so here they give us some information. We want to know the magnitude and direction of the acceleration. So again, we do the whole FBD. We know that his actual weight is 500, but then the weight is measured to be 600 newtons. So while in the elevator, his apparent weight goes up. The scale reading goes up. So we know that our acceleration is upwards. So I'm going to do Fn minus Fg, the normal minus gravity since normal is bigger, plug my numbers in, and end up getting that the elevator is accelerating at 2 meters per second squared up. All right. Here's the next question. Pause the video, work itself, and go in a second. All right, so here we know that the elevator is once again, the elevator is accelerating upwards. So again, my normal force is going to be bigger. That one goes first. So I do this. I kind of do the same setup I did before. The one thing that you'll notice though is I actually went back and I'm using 9.8 as G, just because of the fact that the 9.8 that they're giving me is very clearly supposed to resemble, the acceleration of gravity. So I want to actually use an acceleration that models that, and I end up getting 1,000 newtons. So if you didn't do that, if you still use G as 10, then you would have had 50 here, and this would have been 10 plus 9.8, and you would have ended up getting like 990. So again, not drastically different. And I think this is the last question, so pause the video, work itself, and we'll go in a second. All right, so here we're accelerating downward, so the gravitational force going down is bigger, so that one goes first. Fn is going to be equal to mass times the difference in the accelerations. Plug our numbers in, and we end up getting that the normal force is 500. So that's pretty much it. There's really not much that I could do with elevator rides. I guess the only thing I could do is, try to combine this with like multi-mass systems and some of Newton's other laws, but for the most part, it's kind of approached the problem the same way. In fact, one thing that you should take away from all these questions and all these things in the dynamics unit is that you approach every force problem the same way. You draw an FBD, you identify the direction of acceleration if there is one, and then you do some of the forces, and that's it. The key thing is setting up some of the forces as good as possible, but besides that, there's really not that much tricky with it. All right. So there's three things that I want you to take away from this. The first, like I said, is the fact that when you accelerate, you're going to either feel heavier or feel lighter depending on the direction you accelerate, and that this feeling is related to the apparent force. We can only know the direction of the acceleration without additional information. Just with the bare information of what forces we have and what directions they're going, we can only identify the direction of acceleration, but that's not enough to figure out the direction of velocity. And then again, the scale reading measures the normal force, which changes while your weight is going to stay the same as long as we stay on Earth. That's pretty much it. There's two pictures that kind of show the same idea about, accelerate up, your apparent weight goes up. And then this is just another picture that kind of says pretty much exactly the same thing. What happens when you're in equilibrium, what happens when you're accelerating upwards, accelerating downwards, or in a free fall. But for the most part, it's saying identical things to what I said. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.